Hello, thermodynamicists. I miss you all, and I hope that you are all staying healthy and continuing to learn a lot. So, earlier we talked about one method using moving up and down the line in vapor-liquid equilibrium curves to determine where we'd have coexistence. But the real way we actually do it uses what's called fugacity. And so this whole series of notes for this week, I like the title, What the Fugacity is. What is the fugacity? Well, if we look at the root of the word, it has fuge. It's the root word from an ancient language that means to flee. Fugacity uses the same root word as the root word fugitive. So fugitive and fugacity have that in common. Fugitive is a person that is fleeing the law. So fugacity in thermodynamics, it's the fleeing tendency of a particle. And we're going to spend some time going over how to calculate it. So, like the fugitive, fugacity, or the fleeing tendency of a particle, there is a driving force that leads to both. And very simply put, heat tends to increase the fleeing tendency of molecules and fugitives of the law. When I was studying thermodynamics a while back, we did fugacity in my undergrad chemistry program, and I could not tell you what it was. All the way through grad school, I couldn't tell you what it was. And even now, the exact understanding of fugacity is somewhat fleeing or fleeting. But it's actually incredibly useful. So, for coexisting phases, what we've been discussing, for coexisting phases of a material, the following must be true. Must be true. That is that the Gibbs free energy of the liquid phase at temperature and pressure must be equal to the per molar Gibbs free energy at the vapor phase at a temperature and a pressure. Now, if we go back a number of lectures to our thermodynamic state functions, we can show and recall that a small change in the Gibbs free energy, which I'm just having there, can be broken up into the small changes due to a change in temperature plus the dP term here. So it is to say that Gibbs free energy, as we all know, is a natural function of the temperature and the pressure. And so the small changes here, temperature and pressure, are how we're going to look at what's happening with Gibbs free energy and will ultimately lead to fugacity. From this, you can say that dG under bar, the temperature at constant pressure is equal to minus S. This should be an underbar. And also that partial G, with respect to pressure, with temperature held at constant, is equal to the molar volume. Recall, equilibrium requires that the temperature in both phases are equal. If they're not equal, there will be a temperature gradient, and temperature gradient will cause there to be a flow of energy in all cases. So at constant T, then what we have is that dt equals 0. So the Gibbs free energy between two states at a constant temperature, let's suppose these are defined as the Gibbs free energy at pressure 2 minus the Gibbs free energy at pressure 1 would be equal to the integral of this term here. So this would be the integral from pressure 1 to pressure 2 v under bar dp. We have to do this calculation because initially we don't know where the isobar is. We don't know what P1 and P2 are. So we need to break this into smaller component pieces. Also, if fluid were ideal, then this integral is very, very easy. Then let's write down what the integral would be. The Gibbs free energy at the ideal gas at temperature pressure 2 minus the Gibbs free energy for an ideal gas. Of course, this is our simplest equation of state. At pressure 1 would be equal to the integral from P1 to P2 of RT over P dP. Simply substituting in the ideal gas equation of state for the volume. So, how do we get to fugacity? How does this help us? Why are we talking about ideal gas? Well, in all of these different fluids, with a high enough temperature and in certain regimes, there's an ideal gas behavior, and we can kind of use this to specify roughly where we are relative to an ideal gas. So the next step with this term and with this term is to do the following calculation. Subtract ideal gas situation from real. This becomes kind of like a departure function. How different is this from an ideal gas? Recall, always as P approaches 0, everything is ideal. Because as P goes to 0, there's no interactions between the molecules that causes them to stick to each other. So we have this one additional help that's going to lead us onto our equation for fugacity. Temperature, pressure equals 0 minus Gibbs free energy of an ideal gas at temperature, the pressure equals 0. Of course, because that the real material becomes at 0 becomes ideal, this is equal to 0. This P equals 0 serves as the reference state for future calculations. Okay, so now we can go and do one. We use this reference state and this idea that it becomes an ideal gas, and we calculate now for another temperature, for another pressure. So now we consider a measure at P2 not equal to 0, where P1 is equal to 0. And we calculate, just because we can, the Gibbs free energy at state of temperature and pressure 2 minus the Gibbs free energy of an ideal gas at temperature and comma P2 is equal to the integral from 0 to P2 of V underbar minus RT over P dP. So this is a way now that we are working towards a function that we can use to calculate the Gibbs free energy for material at any pressure P2. We're doing it in this form, and I'll show you in a minute why, because this form has some nice properties that makes this calculation much easier to do. So this is already a more convenient form of calculating G. Okay, so with this more convenient way of calculating G, we are one step closer to calculating fugacity. There's this one more trick that is useful, starting from this equation for the Gibbs free energy difference between a real and an ideal gas material. And that is to use the property of exponentials to kind of stretch this this distribution. You know, this overall doesn't behave well, as you can see. When pressure gets lower, this becomes very large. Maybe it becomes very large in a negative way. You end up with a negative infinity or something like this, which is not great. So to handle some of this poor behavior of the way the math works in this, it's convenient to stretch it and to put this function into an exponential. So we transform it into a new space. And this is done purely for the convenience of the mathematics and the convenience of the computing. So the way that we do this is the definition of fugacity. Believe it or not, which I had serious doubts about it in my own undergraduate training a while back, fugacity is invented to make life easier. And so it's the pressure times the exponential of the Gibbs free energy of your real material minus the Gibbs per molar Gibbs free energy of your ideal gas, temperature, and pressure, all divided by RT. This, of course, up here is dimensionless. Bad writing here, dimensionless. And the units of fugacity, therefore, are pressure, because pressure times the exponential of a dimensionless quantity is still going to be just the term in front, which is the pressure. So fugacity of units of pressure, which is kind of nice, because the fleeing tendency of fugacity, high fugacity, things want to flee. You think about things that are under high pressure as things that want to flee. For instance, you have a bicycle tire with 55 pounds per square inch at gauge pressure, or a champagne bottle, or something like that that's under pressure. And you can kind of almost encapsulate in your mind what's happening there. So like we showed earlier, we're going to use the definition with our reference state of a pressure of 0, which case the region where everything is ideal, to define our formal definition of fugacity. So pressure times exp, I'm going to pull the 1 over RT out in front, integral of 0 to the pressure that you're at, V under bar minus RT all divided by P times dP. And of course here, I say sub in your favorite EOS, your favorite equation of state. There's a related dimensionless quantity called the Fugacity coefficient. And that is simply given the variable phi, and this is equal to the fugacity over your pressure. This is the Fugacity coefficient. This is a dimensionless quantity, and if your fugacity coefficient is a high pressure, I mean, if your fugacity is higher than your pressure, the fugacity coefficient is going to be greater than 1, and if it's lower, it's going to be less than 1. As pressure approaches 0, the fugacity approaches the value of your pressure. Fugacity collapses to becoming like the ideal gas, because as your pressure goes to 0, let me just show you up here, this subtraction between the real material and the ideal gas material the difference will be going to 0. The exponential of 0 is 1, which leaves just your pressure term. So as pressure approaches 0, the fugacity approaches P, which means that the fugacity coefficient approaches 1, which means that the material is approaching an ideal gas behavior. Okay, so this is the introduction, the end of the introduction to fugacity and the fugacity coefficient. In the next video, we are going to talk about how we use these calculations to actually solve for the coexistence of the two states for a real material.